Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosine River College in Sacramento, California. This is a second video in a series on graphing the sine and the cosine if it's your first time seeing the sine and cosine graphs. We have just finished deriving the base graphs for the sine and cosine, and we are now about to go into transformations of these trig function graphs. So stretching them vertically shifting them and reflecting them. That's what we're going to do in this video. And there is a method to the madness, so it is probably a good idea to not consider these the exact same type of transformations that you've learned in the past, even though they are. It's just in the end, what we're going to be doing requires a good knowledge of everything we're going through here. So I would still watch this video, even if you're strong with transformations of functions. So let's start with the amplitude, which is kind of the easiest of all the transformations. So given the function f of x, which is a sine of x, or g of x, which is a cosine of x, the amplitude of f is defined to be the absolute value of that leading coefficient. So of that coefficient a there. It's not really leading, but it's the coefficient a. It's the absolute value of it. So if it was, let's say, for example, f of x is equal to a -3 sine of x, we would say the amplitude, which I always just title amp, the amplitude is the absolute value of that, which is 3. Okay, very fast, very easy. And in fact, here we go with the first example. State the amplitude and graph y equals 3 times the sine of x by hand. And I'm assuming that you do know some transformations from previous work. So the amplitude here is going to be the absolute value of that coefficient 3, which is 3. And we know that that causes a vertical stretch. It's multiplying all the y values of the sine curve by 3. So if you graph this out, normally our sine function, it would start at 0, 0, and would go up, come down, go back up. It would go down to a depth of -1 and go up to a height of +1. But now, and by the way, it would do that in a period of 2 pi, and it is its domain is all real numbers. It has a period of 2 pi, so it would actually continue in both directions forever and ever and ever. But normally we just only draw one period of it, but it does go on forever and ever. But now we have 3 times the sine of x. So all the y values are 3 times what they were before. So instead of having a height of 1, it'll have a height of 3, a maximum of 3, I should say. And instead of a minimum of -1, it'll have a minimum of -3. The x values for our points do not change, and that's critical to note because it is usually when you do vertical stretches in an algebra class, you say, oh, the graph narrows or something like that. And I try to tell my students, that's actually not true. That's an optical illusion. Really what's happening is that it is stretching things vertically away from the x-axis, but because you don't have something that often comes back to the x-axis or oscillates, you can't actually see that stretch. But here you will see that stretch. We have that y value that was at 1 before is now at a y value of 3. And so we get this look here. And the y value that was at -1 is now at -3. The y values that were at 0 stay at 0 because 0 times 3 is still 0. That's just trying to make it pretty. But the blue is the y equals 3 sine of x. The black curve is the sine of x, and it's not needed, so we can erase it. So this is a very good example of what a real true vertical stretch is. It's stretching things away from the x-axis. And in this example, I'm actually taking advantage of both your knowledge of vertical stretches and compressions and your knowledge of reflections. And that's what we know this piece does. It reflects about the x-axis. So normally, this is how I would normally start this conversation. I'd say, well, the cosine curve looks like this. Notice I just quickly jot it down, right? But we aren't dealing with the normal cosine curve. We're dealing with the reciprocal, or not reciprocal, but the opposite of it. So we have to flip that upside down. So let's go ahead and take that curve. Notice I've stopped using the ruler here. We're flipping this graph upside down, reflecting it about the x-axis. I still try to keep it somewhat clean. And I label my key points. It is critical normally. I didn't do it in the previous example, but from this point forward, I will label those key points. There are 5 key points technically, but this very first one is often one that I don't label, 0, -1. Oops. But in this case, it won't be 0, -1 because we are multiplying all the y values by half. So it's not only flipped over, but all the y values are half of what they used to be. So this is a -1/2. This is a +1/2. Well, maybe this is a +1/2. So instead of going from -1 to 1, it goes from -1/2 to +1/2. But that is the graph, going on forever, of the -1/2 cosine of x. Now notice a few things here I want to draw your attention to. When I graph by hand, if somebody told me graph, for example, 5 cosine of x, I have a bad habit of graphing this graph and then saying that's 5 and that's -5. And that's actually not a bad habit. I'm just scaling my axes to fit the curve nicely. So there's nothing wrong with graphing the base curve and then saying, oh, what was the amplitude? 5? Great. That's 5 and that's a -5. Nothing wrong with that. You could totally do that. If you're going to graph 2 on the same graph, like we did in the previous example where we had the sine curve and we had this thing going first, if you're asked to graph 2 on the same graph, obviously you're going to have both scales on there. But generally speaking, I just graph 1 and then label the maximums and minimums the amplitude. Now, just so you don't think that I skipped an example, my next example is to use Desmos to graph this function because I want to showcase something here. So here we are in Desmos, and the first thing that I do is turn off the grid because they're annoying. And I know that as far as y values, I don't need to go crazy, but because I'm going to have an amplitude on this, I'll have this go from -10 to 10. And then the x-axis, I'm okay with it, I guess, going from -10 to 10, but I know that the period of both the sine and the cosine are 2 pi, so I'm going to go from -2 pi, pi gives me a pi, to +2 pi. Also, you can label in there, for some reason that disappeared, but you can label in there -2 pi to 2 pi. I don't know why it disappeared, honestly. But you could also label in there the x-axis. So I could say I want my step size to be pi over 2. And again, my y-axis was supposed to go from -10 to 10, but something weird happened, so let me just fix that. All right. And I don't want to bother with the thing. So now what I'm going to do is move the screen so you can see what I'm doing here. And I'm going to graph f of x is equal to a times the sine of x. And it asks me for a slider at a, and I will totally do that. Now here's a equals 1. Now look what happens when I increase the amplitude. There you go. That's a great view of what happens when you play with the amplitude of the sine graph. Increasing it stretches it vertically. If you wanted to decrease it, it would compress it vertically. And obviously, once you get to 0, 0 times anything is 0. But if you go negative, it gives you a negative sine graph. There we go. There's the sine curve. So you can play with this. Go to Desmos and do this yourself. It's It's really fun to do. And yeah. Now let's talk about midline. Midline is a part of a piece of conversation or a definition that we use within trigonometry because it helps us graph. So the vertically shifted functions f of x equals a sine of x plus d and g of x, which is equal to a cosine of x plus d, are said to have midlines at y equals d. Now you should remember from previous work that d is just a vertical shift. It lifts things up or lowers things by d units. We called it k in the past, but in trig, I just call it d. So let's go ahead and take an example of this. State the amplitude and midline, then graph this function. And notice that the numbers I'm starting to play with here are getting a little bit uglier. Not terrible, but still a little bit uglier. The amplitude here, so amp, is equal to the absolute value of the 3.2, or in other words, just 3.2. And the midline is y equals a negative 4. It's been shifted down 4 units. So that's why our midline is at a negative 4. And then graph that function by hand. Now this one I will actually use a ruler for. And since my midline is 4 units down, I'm just going to make this y-axis a little bit lower there. And not only that, but I'm going to move this ruler down a little bit and we'll kind of leave it off screen until I need it. So here's the x-axis, here's the y-axis. And we're graphing the regular old cosine. Now here's my advice, and I'm going to follow this advice the entire time. You normally would say, oh, I have this cosine curve. It looks like this. Yay. And then you would say, but it's 4 units down. So I'd shift it 4 units down. And the way I teach my students is I tell them, okay, so show me step by step what happens to the graph. In this case, I'm not going to do that. And in fact, in this case, I will erase my work that I just did because I want to showcase to you the exact method that I use for graphing trig functions. So I'm going to grab this, and this will be my midline. I'm about to graph my midline, and I'll use green for the midline. So here's my midline right here. Let me move that off the screen. And this is at a height of negative 4. Once I've graphed my midline, I go ahead and graph the base function. The base function is the cosine function. If it's reflected, then I'll graph the reflection too. But it's not reflected, so I'm just going to graph this base function on my midline. So if that's my midline, I happen to know the cosine curve normally starts above it, crosses it, goes below it, crosses it, and goes above it. So notice I'm trying to be as exact as possible here. So it comes down through here. I'm trying to do this nicely. You see, I'm trying to take my time with it. There we go. I expect my students to be this accurate, actually. All right. There we go. And then what I'm going to do is I'm going to label my key points. I don't tell you to do it here, but I'm telling you to do it out loud. Label your key points. The key points are, this is 0. It ends at 2 pi. Halfway between is pi. And here is pi over 2, half of pi. And here's 3 pi over 2, pi plus pi over 2. Notice I'm almost treating this as if it were the x-axis. It's not, but I'm treating it like it is. Now I'm going to draw the y-axis. The y-axis, so I'm going to grab this bad boy right here. The y-axis occurs at x equals 0. So I'm going to draw the y-axis in. There it is. And now I'm going to label my y, or the maximum minimum y values. Now, we started at a midline of -4. So this height right here is a -4. Remember, the amplitude is 3.2. That means that the distance up, we're going to add 3.2, and the distance down, we're going to subtract 3.2. Well, let's see. -4 minus 3.2 is -7.2. Sorry, I was just making sure that I had everything written out. So that's a -7.2. You just wiggle up and down by the amplitude. -4 plus 3.2 is going to be a -0.8. Now I can draw the x-axis, and the x-axis occurs above a height of -0.8. Not too far above that height, but above that height. So my x-axis might be right around, let me zoom out a little bit, right around here. That's the x-axis. Here's the y-axis. And now I'll make this disappear. Boom. And that is an accurate single period graph of y equals 3.2 cosine of x minus 4. The midline is there as a guide to graph initially. You could leave that midline there or you can erase it. I'm going to leave it there just because I've already labeled where the x-axis is, so that shouldn't confuse anybody. And if you're asked to graph more of it, you can just kind of do that, but generally speaking, they only want one period. So again, how did I do this? I graphed the midline, and then let's see, I'm going to pause so I'll get right there. After graphing the midline, I graphed the base function. If it had a reflection, I would graph it with a reflection, but it didn't have a reflection, so I didn't need to do that. I then labeled the key points. Those are the axial points, or the quadrantial points: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Points, pluralize that. And then let's see. After that, drew the y-axis. Draw and label. How's that? Draw and label y-axis. And then finally, draw x-axis. And this method will get more and more robust as we move forward. But for now, that's what we did. So let's use that same method here. We have a -2 sine of x plus 1. All the mechanical stuff you do before graphing. So the mechanical stuff is stuff like stating the amplitude and the midline. I'll give you those instructions every step of the way here. So the amplitude is equal to the absolute value of that coefficient on the sine, which is 2. That just tells us how far we wiggle away from the midline to get the maximums and minimums. And then the midline, well, that's y equals 1, because it's -2 sine of x plus 1. And now I'll just go through and do what I stated that we should do last time, which is I'm going to graph the midline. Now I'll do that in green again. I'll just scoot that off the screen until I need it again. So this is y equals 1. And now I'm going to graph the base curve. The base curve is negative sine. Don't worry about the 2, because the 2 we're going to label that anyway. But the sine normally, again, if you recall, sine normally looks like that. We're going to go ahead and flip that upside down. I'm going to go ahead and start here. You just pick a point to start at. Don't be sloppy about it, by the way. That is terrible. Well, look at that. And then I say that and I do it. Something like this. Don't be sloppy when you're graphing for your class, because it's lazy. You should be able to be somewhat clean. I mean, this is still slightly sloppy. Technically speaking, that point should be a little bit further over, maybe. There we go. That's a little bit better, at least. But I expect from my students a really good graph. So there we go. That's good. Not great, but it's good. All right. So let's see. Let's label those key points now. So it started at 0. It ends at 2 pi. Halfway between is pi. Halfway between that is pi over 2. And therefore, this must be x equals 3 pi over 2. Then you draw in the y-axis and label it. So let me draw in the y-axis here. There we go. And I still need that for something in the future, so I'll just slide that down. And we're going to label this. Excuse me. If this is a height of 1, so this is y equals 1. Let me erase this. This is y equals 1. And you don't actually need to label the 0 point if it's on the y-axis. That's y equals 1. The highest high here is 1. No, that's not true. It's the amplitude above. So 2 units above. So 1 plus 2 is 3. The lowest low, the minimum, is 1 minus 2, which is negative 1. Again, I am just taking this amplitude and I'm using it to give me the distance between the midline to the maximums and minimums. 1 plus 2, 1 minus 2. Now that I know those heights, I know exactly where the x-axis is. It's halfway in between the negative 1 and 1. Probably right around there. So I'll draw the x-axis in. There's my x-axis. Again, if you want to leave that midline on there, you're more than welcome to. I have no problem with that. In fact, often I kind of encourage people to do that. Usually when I do it, I dash it out. It just takes a bit of time. And because my digital board, it wants to move whenever I do a lot of dashing for some stupid reason. So anyhow, there you go. That is the graph of the negative 2 sine of x plus 1. It's a reflected sine curve lifted up 1 unit, and it's stretched by a factor of 2. That is an accurate graph of it. It does continue on forever in both directions, by the way. It's just I don't draw forever. And finally, in this video, we're just going to go back to Desmos and graph a sine of x plus d. Mainly because we graphed a sine of x before, it'd be nice to see the plus d part. So we're back to our graph, and I'm just going to put in a plus d here, plus d. And now I'm going to add a slider for that as well. Let's go ahead and give a an amplitude of, give the sine function an amplitude of 1. And let me put this in projector mode too, because it's nice to kind of see thicker curves here. So D, that's me moving D there, and A. So there you go. And you can press play and have this go all day long. It'll stretch and do all this stuff for me. And there you go. So these are all the vertical moves, right? You're having these vertical stretches and compressions. I could slow this one down because it seems like it's parking itself a little bit. So there we go. Yeah, that's a good looking graph. All right, so now we will pause this video and come back next time. In the next video, we're going to go through kind of tougher material, which is the period of the function, key points, and step sizes. It's not the toughest, but the period does end up causing an issue for some students, so we'll take a little bit of time on that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.